This video will be covering PixelCNC's use and orient users with the interface, the process for creating CNC toolpaths, and generating CNC G-code programs. We will be producing several different toolpaths demonstrating the range of possible works PixelCNC can be used to create. We will walk through setting up a project, defining its tools, and creating different machine operations which PixelCNC will automatically generate toolpaths for. We will also be demonstrating the built-in simulation system, using it to preview the cuts we can expect from our generated toolpaths when run on a CNC machine or router. PixelCNC's interface is intended to be as simple and straightforward as possible, exposing only the options and parameters that must be considered at each stage of creating a project. Everything concerning a PixelCNC project pertains to generating G-code from an input image. Creation of a project is loosely organized into 4 steps, or modes. Project modes are accessed from the buttons at the top left of the PixelCNC window. Each mode adapts the user interface to expose different project properties and parameters to the user, streamlining the process of creating a project. Most buttons and options will pop up a simple description, or tooltip, when hovered over with a mouse cursor. This helps users orient themselves with the what and where of the user interface. The Project Mode button resembling a photo of mountains brings up the Project Setup mode, which is also the default mode at startup. This mode allows us to load an input image and define our project's dimensions and machine origin. The button for the Cutting Tools mode has the wrench icon and allows us to specify the tools available to our project and its operations. The Mode button for machine operations appears as a dot-to-dot line graph, resembling a toolpath. This is the mode where the operations comprising a project are defined. Operations are the means by which the parameters and settings for generating toolpaths are specified. Both a generated toolpath and its parameters are contained within their corresponding operation. Last but not least is the mode for CNC simulation, which is useful for previewing the results one can expect from a tool moving along an operations toolpath through a piece of material. This mode's button appears as a play icon on a film strip. The other major component of PixelCNC's interface is the 3D view, where we can observe our input images mesh, generated toolpaths, and simulations. The view can be manipulated using the left and right mouse buttons and the mouse wheel. The left mouse button pans the camera view while the right mouse button rotates the perspective. Both scrolling and dragging a mouse wheel zooms the view accordingly. These functions of the left and right mouse buttons can be swapped by toggling swap camera mouse buttons in the configuration menu, and is entirely up to the user's personal preference. Rotating a view revolves it around the point on the XY grid's plane that is in the center of the view, which is always at Z0. The grid subdivisions and appearance can be customized from the Appearance Settings dialog in the configuration menu. This dialog also provides many more options for customizing the appearance of both the user interface and the 3D view. The button bar at the top of the 3D view allows us to set or toggle various aspects and modes of the 3D view. The house button homes the view at a bird's eye vantage point and zooms to fit the current project within the program window. The earth button toggles between drawing 3D mesh geometry as being either solid or wireframe. The overlapping squares button toggles between orthogonal and perspective projection modes. The I button is used to toggle the visibility of any toolpaths in the 3D view, regardless of the active mode. This is useful when toolpaths consist of numerous cuts and rapids, which can obstruct visibility of simulations and make it difficult to discern the quality of a cut. The Stack of Squares button toggles whether or not rendered toolpaths are obstructed by mesh geometry in the 3D view. This can be thought of as toggling whether toolpaths will appear through a mesh, as though it were transparent, or see-through. We will use these different buttons as they become useful over the course of this video. When creating a new project from the File menu, PixelCNC will use the Configured Measurement Units as set on the CNC Cam Settings dialog, which is accessible from the Configuration menu. For this demonstration we're going to be working in inches. Once we've created a new project with the measurement units we intend to use, we can then start by loading an image. PixelCNC supports most common raster image formats. However, there is also basic support for loading vector images that are in the SVG format. The SVG loader renders the vector image to a raster image, with pixel dimensions equal to the size stored in the SVG. This generated raster image is what PixelCNC then uses as the project's input. For the most part, SVG images work fine, but smaller vector dimensions will result in a low-resolution raster image, which is generally not suitable for generating toolpaths or mesh geometry. For the first part of this demonstration, we will use a depth map of a Celtic tree of life for a 3D contour style project. The tree of life is one of the example images included with PixelCNC. In the 3D view we can see the image load, and then the mesh appear once it finishes generating. The status bar discloses the time elapsed to generate the mesh. This height field mesh is only a symbolic representation of our project. PixelCNC's various operations may interpret the input image in different ways that do not necessarily reflect or conform to the displayed height field. In this case, we are creating a 3D contouring project, and can presume that this particular mesh does reflect the final result we aim to produce on our CNC. Now that we have loaded our input image, we can designate the actual size and depth of our project, as well as set our machine origin. We're going to be using a width of 8 inches along the x-axis. Before creating our project, if we had configured PixelCNC to use the metric system, the width would be in millimeters. The project's length along the y-axis is automatically calculated from the image aspect ratio and the project width entered by the user. For now, we're going to use a relatively small depth of 1/4 inch for the Z depth parameter. The invert image option does exactly what you'd expect. It will flip the brightness of each pixel, causing white to indicate depth and black to refer to the project's top surface. Our tree of life image was created assuming darkness indicates depth, so we'll leave the invert option disabled. The auto-scale contrast option is intended for use with images that lack absolute black, or white, or both, but that we want to span the entire Z depth we've established for the project. There are situations where disabling this option would be better suited to a project. If an image does contain both black and white pixels, then this option will have no effect whatsoever. The downscale factor allows working with excessively large images, so users can avoid manually downscaling an image using another program. If users can increase the downscale factor without loss of detail, then it's suggested that they use a downscale of 2 or more. Images larger than about 2050 pixels wide, or tall, generally should be downscaled. This will dramatically speed up PixelCNC by reducing computations when generating toolpaths and mesh geometry, while also reducing the total size of memory allocations. Pressing apply regenerates the 3D mesh with our specified dimensions. Because our image is square, both the width and height are now 8. We can see this at the bottom of the 3D view above the status bar. We can also see that our project Z dimension is 1/4 inch. In the 3D view, the machine origin is depicted as a triple of red, green, blue axis lines. The 3 lines intersect at the machine origin and extend away in the positive direction of their corresponding axis. Their red, green, blue coloration implies the XYZ axis respectively. Red is the x-axis, green the y-axis, and blue the z-axis. Different users will zero their machine on their stock by differing means. For instance, some may zero their machine to the front left of their stock, while others may probe off the 4 sides of their workpiece to find dead center and use that as their machine origin. PixelCNC allows establishing the machine origin as percentages of the project's dimensions. This allows it to be set anywhere within the project's volume or on its outer surface. This makes it easy to set the origin to the extremes of a project's dimensions, or any fraction in between, such as 50% for the middle of a project. We find the top dead center to be the most useful because it allows us to ensure that toolpaths will not be too close to one edge or another. As long as the machine origin is zeroed at the exact center of the stock, we can trust that our cuts will be centered on our workpiece as well. PixelCNC can present a challenge for less capable computers when rendering the 3D view. Depending on the input image's size and complexity, it's not uncommon for millions of mesh triangles to be generated and rendered in the view, which is typically a demanding task for graphics hardware of any caliber. Users can enable Low Poly View Update from the configuration menu, which will render a flat polygon as a placeholder when manipulating the view. Rendering a single polygon keeps the view responsive when interacting with it, especially for slower computers. Now that we've established our project's dimensions and machine origin, we can go ahead and define one or more tools that we plan for our operations to use. Clicking the wrench icon to enter the cutting tools mode, we are now ready for defining our tools. We'll create a few tools one by one, starting with the first tool index. First, we will define a 1/4-inch flat end mill. Flat end mills are a cylinder tool type, which we select from the Type drop-down menu. We'll assume our end mill's total length from tip to spindle chuck is no less than 1.5 inches. This indicates to PixelCNC the maximum depth this tool should be allowed to cut relative to the top surface of our project. The 1/4-inch end mill we'll cut with has no less than 1 inch of flute length, so we'll enter that in for our tool's flute length. Naturally, this tool's diameter is a 1/4 inch. Being that the cylinder tool type covers everything from flat end mills to ball nose end mills, we can enter any corner radius between 0 and the radius of the tool itself. For a flat end mill, we use a corner radius of 0 to indicate a sharp corner edge. Pressing apply, we can see that our custom tool name appears at the selected tool index in our cutting tools list on the left, and we can quickly see our tool specs on the bottom of the 3D view, just as we were able to see our project's dimensions in project setup mode. Displayed is the name of our tool, the diameter, and the total length. We can also see a 2D depiction of our tool's cutting profile in the center of the PixelCNC window, with dimensions labeled accordingly. This is useful for ensuring that we enter the right cutter dimensions, which is important for generating the correct tool paths for a physical cutter's shape. We'll click the next available tool index and define an 1/8-inch ball nose end mill. We'll use a cylinder tool type just like our flat end mill. We'll continue using 1.5 inches as our total tool length. The 1/8-inch ball nose that we'll use has about a 1/2 inch flute length, so we'll enter 0.5. This is a 1/8 inch cutter, so we will enter 0.125 for our tool diameter. Now, being that our tool is a ball nose and not a flat end mill, our corner radius should be exactly half the diameter of our tool, the tool's radius. So we'll enter 0.0625. Pressing apply applies these parameters to the tool index we have selected. Now we have two tools that we can create our operations with and generate toolpaths for. Clicking the Milling Operations button, we can start with creating a typical parallel roughing operation, using our 1/4-inch flat end mill. Clicking the first empty operation slot, PixelCNC automatically gives it a simple name, Operation 1. We'll change that to something more descriptive for our purposes, parallel roughing. Below that, we can then select our 1/4-inch end mill from the tool selection menu, and select parallel as our operation type. For cutting direction, we have 3 choices. Seeing as how this is a roughing operation and we'll be leaving some stock behind, we can get away with using a mixed cutting direction. This will be much faster as it will allow the tool to simply travel back and forth, cutting in both directions. This is ideal for minimizing runtime, but is non-optimal if surface finish is our priority, especially if we're working with a less rigid machine. We'll use the plunge cut engagement mode. This is currently the only means of engaging the tool for a cut in PixelCNC. The ramp and helical engagement modes are still under development, and will become available in a future update. The engage rate is the speed that our tool plunges into the material before beginning a cut. For our purposes, we will use 40 inches per minute. Our actual cutting feed rate can move more quickly, as flat end mills are best suited for cutting horizontally, so we'll set this to 60 IPM. We'll set our spindle rotations per minute at 10,000. When using a 2-flute cutter, at 60 IPM and 10,000 RPM, we'll have a chip load between 2 and 3 thousandths of an inch of material, which is perfectly reasonable. Depending on the machine, bigger chips may induce more flex in the machine, while smaller chips dull the tool more quickly. You'll want to figure out what works best for your cutters and spindle, either by knowing from experience or by using a speeds and feeds calculator. Here's where we get into operation-specific parameters. We're going to leave a bit of stock behind to ensure that our roughing operation doesn't overcut, while also leaving a bit of material for a finishing pass to clean up. This is important for a hobby or tabletop CNC that may not be especially rigid, especially with the decently sized bite our step over will entail. And so for the step size here, we're going to go with 1/10 of an inch, or 100 thou. If this were a finishing pass or we were working with a CNC that is not very strong or powerful, naturally we'd go with something smaller, which would lead to more individual cuts and a longer runtime. By using a 1/4 inch cut depth, the end mill will dig deep and be able to cut the full depth of our project with each cut. This means that there will only be one layer of cuts and no retreading previous cuts to reach deeper into our material. If our project were deeper, a 1/4 inch cut depth would necessitate multiple layers of cuts up until the tool reaches the bottom of the project. Our roughing operations toolpath will never actually cut at a 1/4 inch deep due to our project depth of a 1/4 inch and the 20,000ths of stock we are leaving. The deepest our roughing operation could possibly cut, depending on the loaded image's form, is 0.23 inches or a 1/4 inch minus 20 thou. The maximum depth parameter indicates the depth beneath the top of the project that generated cuts should not exceed. PixelCNC automatically clamps this value between 0 and the project's Z depth. To enable a greater max depth and allow an operation to cut deeper, the project's Z depth must be increased accordingly. The minimum depth parameter has an opposite effect and specifies the depth that cuts must exceed in order for their inclusion in the toolpath. Any length or section of a cut that is shallower than this depth is clipped from the resulting toolpath. This is in contrast with the max depth parameter, which only limits the absolute depth of cuts and does not perform any clipping. The minimum depth parameter acts as a threshold for preventing shallow cuts. Shallow cuts that might skim the top surface can be undesirable with a workpiece that may be stained or painted, for example, or that otherwise has an irregular or uneven surface that's not level with the CNC. Preventing shallow cuts is also useful if the input image has a soft or fuzzy boundary between its topmost surface and areas to be cut. This happens to be the case with our tree of life image, specifically its outer edge, which smoothly transitions into the pattern of weaved roots and branches. For this project we will use a minimum cut depth of 30,000ths or 0.03. This next parameter is common to all operation types. The safe Z parameter establishes the height that the tool should retract to above a project's top surface before making a rapid move to the next cut during an operation. The time that it takes to travel to and from the safe Z height can add up quickly to where an operation with numerous individual cuts could potentially inflate an operation's runtime by orders of magnitude. It's a good idea to retract to a safe Z that's as low as possible without risking crashing the machine or dragging the tool through your material during a rapid move. This can be the case when the material is not evenly flat with the machine, such as with wooden or plastic boards that might be slightly warped or bowed. It's important to take any such misshapenness into account when choosing a safe Z. For this project safe Z we'll use 100,000ths or 1/10 of an inch. The last parallel operation parameter sets the angle of its cut paths. This angle value specifies a clockwise rotation offset. Instead of using a conventional text edit box for typing the desired angle, simply click and drag the angle parameter box up or down. For more precise control over knob values in PixelCNC, hold down the Control key while adjusting. Alternatively, for a faster, more coarse adjustment, hold down the Shift key instead. We're going to keep our angle at 0 for this operation, which means that our cut paths will travel parallel to the x-axis. Having entered all of our parallel roughing operation parameters, clicking Apply will save them into our operation and immediately begin generating the corresponding toolpath. Once the toolpath has completed generating, it will appear in the 3D view with our mesh. Looking at our toolpath in the 3D view, we can see cuts as blue lines and rapid moves between cuts as green lines. These are the default PixelCNC toolpath colors and can be configured from the Appearance Settings dialog in the Configuration menu. Now that we have a completed operation, we can export our G-code, create more operations, or simulate our operation. After clicking the button for entering the simulation mode, we are shown our list of operations just as when we are in the project operations mode. In the 3D view we can see all of our project's toolpaths simultaneously. In this case we only have one operation and its toolpath, so that's all we can see for the moment. Initially there's no simulation mesh because we haven't simulated anything since PixelCNC was launched, otherwise we would see the last simulated cuts resulting mesh here. Selecting our operation automatically generates a simulated cut of all preceding operations, up to, but not including the selected operation. In this case there are no previous operations, so we start with a flat, uncut mesh. We can alternatively click the Skip Ahead button next to our operation to skip to the simulated result after it is completed cutting in its entirety. The Skip Ahead button produces a higher quality simulation mesh than what is generated by the live cut simulation, which utilizes a faster but lower quality algorithm to maximize simulation performance. With our parallel roughing operation, our toolpath is somewhat obstructing our view of the simulation. By toggling toolpath visibility, we can prevent toolpaths from being rendered. This provides an unobstructed view, making it easier to see what our simulation actually looks like. On the right side of the screen we can see some operation properties, the name, type, and tool used for this operation, along with a progress slider that simultaneously indicates and manipulates the simulation's progress for the selected operation. We can also see basic controls for playing, pausing, and stepping forward or backward through the simulation. The speed knob adjusts the live simulation increment size. Smaller values will produce smaller simulation updates, which are faster to generate, while larger values will simulate larger chunks of the toolpath being cut at a slower rate due to the extra computation involved. Users can adjust their simulation quality settings from the configuration menu. It's a good idea to use the smallest sufficient simulation resolution possible to minimize computation and maximize the simulation update rate. While a higher simulation resolution will produce increased visual fidelity and cut accuracy, the computation cost increases exponentially, which is reflected by the time it takes for simulation updates to generate. The mesh quality setting affects the coarseness of the 3D mesh by controlling the threshold at which geometric subdivision occurs, which is the means by which the shape and form of the simulation depth map are conveyed geometrically. It is recommended users keep this as low as possible without sacrificing simulation fidelity too much to prevent excessive computations and memory consumption when running simulations. Certain situations may call for a simulation with more accurate geometry and benefit from increasing the mesh quality setting, such as a VCarving with fine details and features. By this point we've successfully created a simple project which we can save or export G-code for from the File menu. Instead, we're going to create a finishing operation using the 1/8" ballnose tool that we defined earlier. Returning back to Operations mode, we can select the next unused operation slot. First we'll name this operation Spiral Finish. Then, we will select the ballnose cutter for our finishing toolpath to be generated for. Next, we could choose to create another parallel toolpath and use a small step size, but just to mix things up we're going to use the spiral operation type instead. The spiral operation is a contouring operation just like the parallel, chevron, and labyrinth operations. The difference between these operations is the shape of their toolpaths, but they all interpret the input image as a height map. We'll use the climb cut direction, which tends to produce a better finish, and using this specific version of PixelCNC, plunge is the only engage option available to us for now. With a smaller tool we will need to reduce our engage and cutting feed rates. We're going to use the engage and cutting feed rates we used for our 1/4" roughing operation, reduced by half. That's 20 IPM for our engage rate, and 30 IPM for our feed rate, and we'll keep the spindle at 10,000 RPM. Since this is a finishing operation we're not going to leave any stock behind, so we'll set leave stock to 0. This will result in the operation cleaning up the material left behind by our roughing operation and our ballnose cutter following the contours of our tree of life as closely as possible. To minimize the size of our scallop ridges we'll use a 20,000th step size. To get a smoother finish we could go smaller, somewhere between 5 and 20 thousandths, but for this demonstration 20 will serve our purposes. We'll let the ballnose cutter reach the full depth of our project and perform only a single pass. This is because we won't actually be asking it to cut through a 1/4" of material once the parallel roughing operation removes most of it. So we will keep our cut depth at 0.25 inches. To make sure we actually cut to the bottom, we'll keep the max depth at our project's seed depth of 1/4 inch. Then, we'll threshold the tool path at 30 thousandths deep, just as we did with the roughing operation, to prevent the tool from climbing up into some shallow cuts. Lastly, we'll keep our rapid height at 100 thousandths. Hitting apply, we see our operations toolpath generate. The resulting toolpath comprises one long continuous cut in a counterclockwise direction. We can now return back to the simulation mode and observe our new operation's approximate effect on a piece of material. We can either skip ahead and see the final result, or we can watch the cut unfold with a live simulation and see the interaction between our finishing toolpath and rough cut material that our parallel operation leaves behind. With our two operations ready to go, we can save our project and also export our G-code. For a machine with an automatic tool changer, we just have to make sure that tool index 1 has our 1/4 inch and mill, and tool 2 is our 1/8 inch ball nose cutter. For the rest of us who are not so fortunate, we have to export our operations individually as separate CNC programs. In operations mode, we can toggle individual operations from being included in our exported G-code. To first export our parallel roughing operation, we can click the right Enable button here on our spiral finishing operation to prevent it from being included in the G-code we export. You can see here that the icon changes to a no symbol. Now we simply export our G-code from the File menu, and the result will consist only of our roughing operations G-code. Now we can swap the right Enable toggles on our operations to ensure that only our spiral finishing operation will be included in our exported G-code. Once we have both of our operations situated, we will go ahead and export our finishing pass as a second CNC program. For the next part of this video, we're going to create a new project. We will again be using inches as our system of measurement, but this time we're going to load the included Cupcake example image. Our new project will have the same dimensions and machine origin as our Tree of Life project. PixelCNC automatically enters the most recently used values for most parameters. This means that we won't be required to enter our size and origin once we've loaded the image. We're going to be creating a VCarving from the Cupcake image. We will also be adding a thin outline to provide a more stylized appearance. Both operations can be performed using a single V-bit cutting tool, which is what we'll be defining in the cutting tools mode first. As before, we first select an empty tool index, name our tool, and can begin defining our V-bit and its dimensions. We'll assume that the physical tool will be about 1.5 inches from tip to chuck, but for the operations we'll be creating, this isn't really much of an issue. The total tool length only needs to be longer than the flute length, which will be automatically calculated from the diameter and bit angle we provide. The bit we're using has a 1/2 inch diameter and a 90-degree tip angle. Pressing the Apply button, we can see that our tool has been entered into the tool index slot we selected, and we can also see the 2D profile of our cutting tool along with the calculated flute length, which determines how deep we'll be able to cut horizontally with this tool. Moving on to our project's operations, we'll click the first unused operation slot, name our operation, and make sure our tool is selected. To create our VCarving operation, we use PixelCNC's medial-carve operation type. If we were using a ball nose cutter, we would be creating a VCarving instead. The medial-carve is not a 3D contouring operation like the parallel and spiral operations. The medial-carve reproduces 2D shapes by cutting along their medial axis while varying the depth, which widens and narrows the cut at the material surface. Medial-carving is extremely useful for producing cuts with interesting unvaried depth without the need for a depth map like the Tree of Life image we used previously. A simple black and white, or binary image is sufficient. To ensure the best finish possible, we'll use the climb cutting direction. Our cutting gauge will remain at plunge, but as you'll see, the medial-carve naturally ramps the cutter into the material anyway. We'll use a 30 IPM engage rate and a 40 IPM feed rate with a spindle speed of 12,000 RPM. With a medial-carve operation type, the step size parameter indicates the distance to offset the tool path from the actual medial axis to ensure clean cuts on each side. Setting this between 1 and 5 thousandths should work fine. We'll use a step size of 2 thousandths. Our cut depth should be able to reach the full extent of our cutter's flute length, so we'll set this to 1/4 inch. If we were worried about too much force on our machine at this cut depth, we could use a smaller one, and our generated toolpath will include multiple cut passes to retread any cuts until they reach the depth necessary to recreate the shapes in our image. We'll also set our max depth to 1/4 inch. Allowing shallow cuts is important for reproducing sharp corners in a V-carving, so we will set our minimum depth to 0 to allow shallow cuts. The threshold value allows us to specify the brightness level between light and dark to use as the boundary delineating the shapes we wish to V-carve. For most images, leaving this at exactly half, or 0.5, is perfectly suitable. Clicking apply, we will see PixelCNC generate the boundaries that it will carve, and then the resulting medial axis toolpath that will carve out material within those boundaries. The smoothness of the initial polygon boundaries is important for generating an economical medial axis toolpath. We can adjust the settings which control toolpath generation from the CNC CAM settings dialog in the configuration menu. The toolpath simplify parameter controls the amount of toolpath segment collinearity that is acceptable. Increasing this value produces fewer segments, or linear moves, which will cause shapes and contours to be recreated less faithfully, and result in a polygonal appearance. Decreasing this value will increase the number of segments generated, resulting in an increase in both the time it takes to generate a toolpath, and the total size of generated G-code. The segment minimum length parameter indicates the shortest allowed segment length in generated contours and cut paths. Increasing this length reduces path complexity and computation time. This also reduces the total number of linear feed commands in generated G-code. Decreasing this value may result in more accurate cut paths, but may become undesirable after a point due to input images being of a finite resolution, and tracing individual pixels is probably not what users are hoping for. Coarse toolpaths will result from increasing this parameter by too much. A value between 10 and 25 thousandths is best. The segment maximum length parameter controls the opposite of the minimum length parameter, preventing extremely long contour and toolpath segments, which can be problematic in certain cases. Keeping all of these parameters at their original default values is recommended, but you may find it useful to adjust them under certain circumstances. In the case of a medial-carve operation, using too small of values for the toolpath simplify and minimum segment length settings can result in a medial axis that has many extraneous spines projecting from it. This is a good indicator that the settings for toolpath simplify and segment minimum length be increased. When simulating our V-carving operation, all appears well and good. Now we'll move on to creating an outline operation for decorative purposes. This operation will also be using our V-bit, but we will choose the outline operation type. We'll leave the cutting direction set to climb, and also be using the same feeds and speeds as our V-carving. The outline operation allows us to generate cuts following a boundary dividing between light and dark areas of our image. We can set an offset distance from this boundary using the step size parameter, where a positive value indicates an offset into the light areas, and negative values offset into darker areas. This makes the outline operation type useful for creating profiling operations. We're going to offset our boundary by 1/8 of an inch. We will leave the cut depth parameter at 1/4 inch, but we're going to clamp all cuts with the operation's maximum depth set at 50 thousandths, which is the depth that we want to cut our outline. The minimum depth parameter is irrelevant here as we're cutting at a fixed depth for the entire operation. The 100 thousandths safe C height is perfectly acceptable for now. The threshold value for our outline operation works the exact same way as with a medial-carve operation, specifying the threshold between light and dark to regard as our outline boundary. We'll keep this at 0.5. By hitting apply, our outline operation is created and its toolpath is generated. Returning to simulation mode, we can press the skip ahead button on our outline operation to see the sum total of both our operations. Our outline adds a nice groove that's 100 thousandths thick and a uniform distance from the edge of our V-carve. Now we can save our project and export our G-code as one long program to be run with a 1/2 inch diameter 90-degree V-bit. This concludes the demonstration of PixelCNC. Thank you for watching.